What's up everyone, my name is Vincent and today I want to take a look at partial fraction integration. Now these are the three examples that we're going to go through and let's get started. For questions like this, the most important thing you have to be able to distinguish is that the factors that you have in the denominator, you want to know if they break down into linear factors or if you're going to have any leftover factors that are quadratic but not factorable. And when we look at x squared minus 9 in the denominator, x squared minus 9 is a difference of two squares. And it does in fact break down to x plus 3 times x minus 3. So since this quadratic does break down to linear factors, for this question we're going to be in case 1 and we're going to be able to split this up nicely. So the resulting equation that we're going to set up is here. Alright, so then the rest of the problem here is us using our algebra skills to solve for the constants a and b. So to solve for a and b, we're going to go through this equation. All right, now from this equation, we're just looking at these expressions without the integrals. To solve for a and b, we need to make these last two fractions here have matching denominators with 3x minus 2 over x squared minus 9. So to have these denominators all match, we're going to multiply this fraction by x minus 3 over x minus 3, because if we were to multiply x plus 3 times x minus 3, it would equal x squared minus 9. And then this last fraction here, we'd have to multiply by x plus 3, and then this last fraction would have a denominator that matches the other two now. And once we get to this step here, essentially like all these denominators just kind of cancel out, and what we're left with is the following equation. Now to solve this equation for a and b, we could distribute, and I'll show that method in a later question, but there's a really nice way to solve for a and b where we pick out test values. And the test values that make the most sense to use are ones that make these factors x minus 3 and x plus 3 equal 0. And x equals 3 will make this middle term here cancel out completely. So when we plug in x equals 3, on the left side of the equal sign, we'll have 3 times 3 minus 2 is now equal to a times 3 minus 3 is 0. And this term just cancels out. And then we have plus b times 3 plus 3 is 6. So then the resulting equation that we have to solve, we're going to have 9 minus 2, which is 7, equal to 6b. And if we solve for b here, we're going to have b is equal to 7 over 6. So this is one of the terms that we need. And now we're going to plug x equals negative 3 into this equation here, and that's going to help us solve for a. So when we plug in x equals negative 3, we're going to have 3 times negative 3 minus 2 equals, and we have a times negative 3 minus 3 is negative 6, plus b times, and when we plug in negative 3 plus 3 is 0. So that's why this test method is pretty nice, because it just gives us the values for a and b directly. And then here we're going to have negative 9 minus 2 is negative 11 equals negative 6a. And when we solve for a, divide both sides by negative 6, we're going to have the quotient of two negatives. So this is going to work out to a equals 11 over 6. But now once we solve for the constants a and b, we're going to plug them back into these integrals on the right and we'll be able to solve this question. Okay, so now we're ready to plug in the constants. So when we plug in a equals 11 over 6, that's a constant, so we could just bring that out in front of the integral and write 11 over 6 times the integral of dx over x plus 3. Plus, and b is 7 over 6, which is a constant that we could bring out, and we have the integral dx over x minus 3. Now in this case here, we could do a u substitution for both of these integrals, but if you let u equal x plus 3, the derivative of x plus 3 is 1. So in situations where you have a u term with the derivative of 1, you could just go ahead and take the antiderivative and it's not going to matter. So we're going to have 11/6 times natural log absolute value x plus 3. And then for the second integral, we're going to have 7 over 6, and we're going to have natural log absolute value x minus 3. And then don't forget the plus c at the end. That's an annoying way to lose a point. And this is our final answer to the first question. Now for the second question here, we look at this quadratic on bottom, and the main question is this factorable? Well, we could try the AC method, and if we look, 5 times 2 is 10, so we're asking ourselves what two numbers have a product of 10 and a sum of 7, and those numbers are going to be 5 and 2. So the denominator can be expressed as 5x squared plus 5x plus 2x plus 2. So we're just basically splitting the 7x in the middle up to 5x plus 2x. So now when we do factoring by grouping, we're going to have 5x times x plus 1 plus, and the greatest common factor of the last two terms is 2, and we'll have an x plus 1 left over. So then from here we take out the x plus 1, and we're left with 5x plus 2 and the other set of parentheses. So the denominator is factorable, and we have linear factors, so we're still in case 1 here. So for this integral, we could set up the following equation. So to solve for the constants a and b, we need to solve the resulting equation. And when I say we need to solve this resulting equation, we're going to be solving it for the constant a and b. So the strategy we're going to use is the same as in the last problem, that we need this denominator to match the one on the left. And the only factor that's missing to make it match is 5x plus 2. So if we multiply this denominator by 5x plus 2, we need to do the same thing up top. And then for the last fraction here, to make 5x plus 2 match the other denominators, this one is missing a factor of x plus 1. And now all the denominators match, so we could cancel them all out, and we'll be left with the following equation. But you'll notice that this time around, I distributed the a to 5x plus 2, and that left us with 5ax plus 2a. And for the last fraction here, we distribute b, and we get bx plus b. And when you solve an equation like this, I'm going to show an alternate method. You need to set up an equation that relates all of the x terms together. So we have 2x, we have 5ax, and we have bx. So since these are all of the x terms, we could isolate them and set up an individual equation of 2x equals 5ax plus bx. And the remaining stuff here, if we look, we're left with 5, 2a, and 1b. And those are all constant terms, so those could be set up in a separate equation where we have 5 is equal to 2a plus b. But if we look at the equation on top, all three of these terms have a common x. So if we divide everything by x, the x's could cancel out, and we'll be left with the following system. And I'm just going to write it a little bit different. I'm going to write the bottom equation on top. We have 5 equals 2a plus b, and on bottom we have 2 equals 5a plus b. And to solve this system of equations, we can multiply the bottom equation by -1. And now what we'll have here is 5 equals 2a plus b, and on bottom we'll have -2 equals -5a minus b. So now when we add these equations together, we're going to have 3 equals -3a, and then b plus -b cancels out. So then to solve for a, we just divide both sides by -3, and this tells us that a is equal to -1. And if we want to solve for b, we could just plug a equals -1 into any of these original equations. So let's say we plug it into the 5 equals 2a plus b. Well, if we have 5 equals 2 times a plus b, we replace a with our solution -1, and then solving for b, we have -2 on the right, and if we add 2 to both sides, we'll have b is equal to 7. So with these two values for the constants, we could plug in now and answer this question. So if we plug in now, on the right side of the equal sign, a equals -1, and it's a constant that we could bring out in front. We'll have -1 times the integral of dx over x plus 1. And now we have plus b is 7, which we could bring outside the integral, and we'll have dx over 5x plus 2. Now, these are both u sub situations, but they're questions that you could do in your head with enough practice. This one, I'm not going to do a u sub because when u equals x plus 1, the derivative of x plus 1 is 1, and that's not really a nice situation to do a u sub. So for the first part of this question here, we could go ahead and say that our answer is negative natural log absolute value x plus 1. But for this second piece here, we'll go ahead and define u equals 5x plus 2. And then du is equal to 5 dx. So when we solve for dx, we're going to have du over 5 equals dx. So what that tells us is that the second integral we could say is plus 7. And in the denominator, we're going to have u. And in the numerator, dx is equal to du over 5. So the over 5 we could bring outside, because this is technically 1/5 times du. So the 1/5 attaches to the 7 and makes 7/5. So then here to close this out, our final answer here, we're going to have negative natural log absolute value x plus 1 plus 7/5 natural log absolute value of u, but we'll make a big space here, and then plus c at the end, and u is equal to 5x plus 2. So this is our final answer to the second question. Okay, for this last question here, remember, we have to look at the quadratic on bottom and ask ourselves, is it factorable or not factorable? And there are a few ways you could determine if a quadratic is factorable. But if you look at x squared plus 2, x squared plus 2 has a y-intercept of 2, and it opens upwards. So the sketch looks something like this. And this tells us right away that x squared plus 2 is not factorable because it has no real roots. So the one way is to sketch the quadratic and see if it hits the x-axis. The second way would be to look at the roots of x squared plus 2. And since the roots are imaginary, because if you solve x squared plus 2 equals 0, you're going to have roots of plus or minus. So this would give us x equals plus or minus I radical 2. So because we have imaginary roots here, this quadratic on bottom is not factorable. Well, since this quadratic is not factorable, this is going to bring us down here to case 4. So we're going to set up the following equation. All right, so in this formula here, our constants are going to be A, B, C, and D. Now, I know in this set here with the notes, we have A1 all the way up to A sub k, but the alphabet only goes up to 26 letters, and if k is bigger than 26, then we're going to run out of letters in the alphabet. So that's why they use subscripts here. But since we only have a power of 2, we could just go up to A, B, C, D. And for this, to solve for the constants, we have to look at the following equation. Now in this equation here, the only fraction that doesn't have a matching denominator is the middle one. The other ones have denominators of x squared plus 2 squared. So for this middle fraction, we're going to have to multiply the numerator and denominator by another factor of x squared plus 2. And this will ensure that all of them do in fact match. So in this case here, all the denominators wipe out, and we're going to be left with the following equation. So for this question here, we have a little bit more algebra to do. We have to deal with this middle term here. We have to expand it. If we want to use that test value method, it's not going to work here because there are no real numbers that are going to make x squared plus 2 go to 0. So we have to just go ahead and do the algebra here. And if we do in fact expand this, we have ax times x to the second giving us ax cubed. And then when we multiply the last terms, we have plus 2ax, and then when we distribute b, we're going to have bx squared, and then at the end the constant is going to be 2b, and then we have this plus cx plus d at the end. So in this question, we just have to look for terms that have the same power of x, And if we look at, let's say, the x to the third first, on the left side of the equal sign, we have 8x to the third. And on the right side of the equal sign, we only have ax to the third. So what this allows us to say is we could set up the following equation. We're going to have 8x to the third is equal to ax to the third. Well, the only way this equation is going to be true is when a is equal to 8, because the powers of x match, so they just cancel out here. And what we can conclude here is that a is equal to 8. Let's say we look at the x squared terms next, because we took care of x to the third. On the left side of the equal sign, we have no x to the second terms. And on the right side of the equal sign, we only have bx squared. So what we take from this is on the left side, we have 0x squared terms. And on the right side, we have only a bx squared term. So in this situation, the only way this works out, because the x squares cancel, is when b is equal to 0. So sometimes this can happen. We could have a 0 value for one of our constants. And then the next thing we should move to is the x terms. So if we look here, our x terms are, we have 13x, and then here we have 2ax, and we have cx. So if we extract all of that information, that's going to give us 13x equals 2ax plus cx. Sorry, that wasn't maybe the best thing to highlight with. This was a cx here, but that pink highlighter kind of erased it. And if we get rid of all the x terms here, because they all match, we could just get rid of them. And we make a substitution for a is equal to 8. Now we have the equation 13 equals 2 times 8 is 16 plus c. And this tells us that c is equal to -3. So now we have our third constant, so then we're just going to solve for the last one. So to solve for the last constant, now we're going to make use of the last term, which is the constant term. And if we look here, the left side has no constant term, and on the right we have 2b plus d are the constant terms. So once again, on the left, we said that we had no constants. There was like no single number there, so we have a 0 constant on the left, and on the right we have 2b plus d, but we were already told that b is equal to 0. So when we plug in b equals 0, we're going to have 0 is equal to d, which tells us that the last constant d is equal to 0. So now we're going to plug this into our equation from before and solve this question. Okay, so if we make this substitution here, in the first fraction we have ax plus b. So a is equal to 8. B is equal to 0, so we're just going to write 8x. We don't have to write plus 0 over x squared plus 2 dx. And then for the second fraction, now we have the integral of, and c is equal to -3, so we have -3x over x squared plus 2 squared. And one thing to point out, I know we have a plus d here, but d is equal to 0. So we're only going to have c is -3, so -3x plus 0 is just -3x. And don't forget to write these dx's, they are important. So then to close this question out, we're going to make a u substitution, and we're going to let u equal x squared plus 2. And it's pretty convenient for these repeating factors, because when we do a u substitution, we could use it for both of these integrals. But we should note here that du is equal to 2x dx, which tells us when we solve for dx that du over 2x is equal to dx. So when we make the substitutions now, the 8 could just come out here. We're going to have 8 times the integral of x over u, and dx is equal to du over 2x. And you'll notice here the x's cancel out. And then the next integral, we're going to have plus, and I could get rid of that plus. I'm just going to write -3. I'm going to take that -3 out from the numerator, and that's going to change this addition to subtraction. So we have -3 times the integral of, and we're left with an x in the numerator. In the denominator, we're going to have u squared, because x squared plus 2 is u. And then dx is equal to du over 2x. So once again, the x's cancel out. And then we're just going to rewrite this a little bit simpler. This is now 8 divided by 2 is 4. So we have 4 times the integral of du over u. And now we have minus, the denominator 2 is going to come out as 3/2. Well, when it attaches to the 3, it's going to make this 3/2. And we have u to the second on bottom, which we could bring up as u to the negative 2 du. To be careful, don't say something like natural log absolute value u squared, because the only time you could use natural log for antiderivatives is when it's du over u to the first. So then here, to close this out, this is going to be 4 times natural log absolute value of u, and now we have minus 3/2 u to the negative 2 plus 1 is negative 1, and when we divide this expression by negative 1, it changes the operation from subtraction to addition, and then we've got a plus c at the end. So the last thing we need to do is just plug back in for u, and we'll be done. So in the next line here, we've got 4 times natural log absolute value x squared plus 2 plus 3/2, and we've got x squared plus 2 to the negative first power plus c. But one tiny detail here, just make this observation: x squared plus 2 is always positive, so the absolute value can drop here. The absolute value is only needed when the expression on the inside could be positive or negative, but if the expression on the inside is always positive, then we could just change this to parentheses and say 4 times natural log x squared plus 2, and then we write the rest. We've got 3 over 2 times x squared plus 2 to the negative 1 plus c, and this is our final answer simplified. Okay, well, this is going to conclude this video on partial fraction integration. If you found this video to be helpful, please click the like and subscribe buttons below. It really helps me grow the channel. And if you got any requests, just leave the topics in the comment section below. And thank you for watching.